Hello, good afternoon, good morning to everybody. Shall we start? It's already the time. So welcome to the Energy System Planning for Sustainable Development in Thailand, Webinar Series 2. Power System Optimization for Capacity Expansion Planning and Sector Coupling with PyPSA, Case Studies and Demonstration, which is organized by the Joint Graduate School of Energy and Environment at King Mongkut University of Technology, Thonburi, under our collaboration with USAID Southeast Asia Edge Hub, implemented by Tetra Tech. This webinar is the second in the series after our first seminar, which was held on April 25th on the topic Energy Optimization Modeling and Investment Strategies for Generation, Transmission, and Distribution. I would like to give a brief background of the organizing of this webinar series. During the past years, JGC, with a strong support from USAID Southeast Asia Edge Hub, has carried out capacity building and knowledge sharing activities. One key activity is the development and launch of the energy modeling and analysis course, which was structured to include the energy and power system modeling, from the demand to generation, transmission, and least cost optimization through PyPSA, or Python for power system analysis. And finally, the holistic energy system planning. Energy system optimization modeling is a powerful tool that can help policymakers and planners make informed decisions about the design and operation of energy systems. The model can be used to identify optimal strategies for meeting energy demands while minimizing costs and environmental impacts, which will be useful for strategic planning and investment for generation, transmission, and distribution systems. While the webinar series 1 highlighted the importance of and benefits of energy system optimization modeling, as well as introducing the key tools commonly used, such as Python for power system analysis or PyPSA. This webinar aims to showcase example case studies for energy and power system optimization using PyPSA, as well as renewable energy zoning for cross-cutting decision support. Could you go back to agenda of the webinar series? Okay. So this webinar will discuss by 4 expert speakers from Tetra Tech and KMUTT on some example case studies using PyPSA to analyze energy system planning and policy under different scopes of application, and to demonstrate how PyPSA can be used to enable and study sector coupling in energy system modeling. Before we start the technical session, I would like to inform you the housekeeping rules for this webinar. Please mute your microphone during the webinar, and there will be a Q&A session after the presentation. If you have any question, you can type using the chat features or raise your hand, and then you'll be invited to turn on your microphone. And this webinar will be recorded and posted on the JGSEE website and the Facebook of JGSEE CEE. Okay, now I would like to invite all the speakers and participants to turn on your camera so that we can have a group photo, please. May I ask
okay.
Kun or assistant? Yeah.
Okay. 1, 2, 3. I need another one. Please wait a minute. Sorry. Okay, finish. Thank you.
Okay. Thank you very much. Okay, so before we start the presentations by the four speakers, I would like to provide some recap from the first webinar. Okay, so this is the agenda of the first webinar. So we started off with the first speaker from EGAT, who talk about investment strategies for generation and transmission expansion, referring to Thailand carbon neutrality to 2050 and net zero greenhouse gas emission 2065 target with an increase of renewable share more than 50%, improvement of energy efficiency more than 30%, and promotion of electric vehicle according to 30 at 30 policy, and restructuring of energy industry into 4D1E guidelines, which include the digitalization, decarbonization, decentralization, deregulation, and electrification. EGAT has a carbon neutrality 2050 plan using PyPSA, which are source transformation, sink, co-creation, support measure mechanism. For the power development plan, the Thailand PDP 2018 revision 1 is based on energy security, economy, and ecology principle, which include the natural gas plant with the installed capacity reduced from 56% in 2019 to 42% in 2037. The current and future power purchase from Lao PDR and transmission system interconnection by 2030, 2032, and 2033. The hydro floating solar hybrid system with a potential of 2,725 megawatt from 16 projects between the year 2020 to 2037. Expansion plan of EGAT 500 kilovolt transmission system, and the EGAT challenges and barriers including power system flexibility, operation of future grid, power grid infrastructure, and market design for carbon neutrality. And then the speaker from the PEA, or Provincial Electricity Authority, talked about distribution network investment strategy. The PEA has the strategic plan to leverage efficiency and reliability and develop smart grid, prepare for electricity market liberalization, and strive to become the leader for social and environmental sustainability. We also learn about PEA's project feasibility study criteria, such as demand forecasting, unit cost, existing asset data, current and historical power quality data, network models, and other constraints, as well as planning criteria, which is the load and voltage, constant configuration of substation and network, and so on. The speaker also gave an example case study in small city in Chiang Mai, where financial and economic analysis are compared among different plausible scenarios. So after listening to the status and plan of power system from the Thai power utilities, the third speaker from Tetra Tech elaborated the challenges of renewable energy integration and grid infrastructure interventions, including power system flexibility, grid stability, unplanned growing of distributed energy resources, land use conflict, social impact, and material disposal. On the other hand, increasing renewable energy share also created positive impacts such as increased use of clean energy, reduced greenhouse gas emission, and job creation. And in the last presentation of the webinar 1, the speakers from DataTech focused on the international experience on energy system least cost investment optimization and how it helped plan the country's strategies to be more energy resilient, some best practices and lessons learned, and challenges of energy system planning were shared. The speakers also introduced about PyPSA, what PyPSA can do and its advantages in comparison with other energy modeling and power system tools. The record of the first webinar is available for watching. Please visit the JGSEE website and Facebook JGSEE CEE. Okay. So as mentioned today, we will learn more how PyPSA is used to model, analyze, and optimize the energy systems. Our first speaker, Mr. Paul Tusen from DataTech, will present on the topic power system optimization, a case study of Barbados and Uzbekistan. So Mr. Paul Tusen, the next 30 minutes is yours.
Thank you. I'm just waiting for the slide. Good morning, ladies and gentlemen. I hope you can hear me okay. My name is Paul Tusen. I'm Energy Sector Director at Tetra Tech. I'm going to be presenting 2 case studies on power system planning and integrated resource and resilience planning. The first country is Uzbekistan, and the second country is Barbados. Next slide, please. Next slide. You can go to the next slide. Next slide, please. Key features of the Uzbekistan energy system are as follows. It is well connected with its Central and South Asian neighbors, Kazakhstan, Tajikistan, Kyrgyzstan, Afghanistan, and Turkmenistan. And it's also connected to Russia in the north through Kazakhstan. There are moves towards a Central Asia, South Asia regional market called CASAREM, C-A-S-A-R-E-M. At the time of the study, Uzbekistan included aging gas steam power plants and hydro power plants, and included no renewable energy power plants or energy storage power plants. Due to Uzbekistan's connection to the larger Kazakhstan and Russian power systems in the north, the Uzbekistan generators were all operating in power control mode and not in frequency control mode, as frequency governing was largely undertaken by Russia. A relatively simplistic intertrip scheme was in place to trip load on the loss of Uzbekistan generation and when intertie flows exceeded contracted levels. No automatic dispatch system, ADS, or automatic generator control system, AGC, was in place. A power system planning study was commissioned by the Asian Development Bank, ADB. A demand forecast was undertaken together with a generation planning study and a transmission planning study. Electrified transport and the transport component of the energy balance was not considered. The study was done a few years ago. Next slide, please. From the figure, it can be seen how well connected Uzbekistan is with its Central and Southern Asian neighbors, Uzbekistan is the green country in the center. As mentioned, Central Asia is connected to the large 300 gigawatt Russian power system north of Kazakhstan. And Kazakhstan is to the north of Uzbekistan. Next slide. This figure shows the high voltage transmission lines connecting the different countries. The lines are shown in bold red. Over the years, there have been political tensions between some of the Central Asian countries, and the transmission interconnectors have been opened and flows between the connecting countries terminated. Next slide. As part of the master plan, we undertook a demand forecast and we generated high, medium, or base, or expected, and low demand forecasts to 2038. The demand forecasts were primarily based on forecasted GDP from the Ministry of Finance and the historical and projected correlations between annual energy and GDP. The slide, although the slide shows average annual demands, the demand that were undertaken at a much higher resolution to give hourly demands throughout the time horizon. Next slide, please. Carbon pricing by request of the client was not used in the analysis. The figure shows the megawatt capacity results of the least cost generation planning analysis based on the demand forecast. Uzbekistan is mostly desert and dry and has significant solar resources. So of note in the figure is the significant growth in solar PV, yellow bars, going up to 2038. Wind resources are less prominent in Uzbekistan, but they also grow to 2038, the green bars at the top of the figure above the yellow bars. Battery energy storage complements the growth in renewable energy, the green bars. Natural gas, the gray bars, initially has an increase due to existing capacity shortages. At the time, Uzbekistan was load shedding. This increase in gas capacity is associated with retirement of old inefficient gas generation assets and the commissioning of new gas turbines and reciprocating engines, internal combustion engines, ICEs. Due to the retirement of generation, a net generation capacity remains, shown by the bold red line. Next slide, please. This figure shows the energy in megawatt hours results of the least cost energy plan. The energy requirement of gas, the gray lines, reduced to 2038, while the energy requirement of solar, gold bars, wind and hydro and imports increase. Some legacy coal energy still remains in the plan. Going forward, if further IRRP studies are undertaken, it is feasible that the coal and gas energy allocations could reduce further. Next slide, please. This figure shows the evolution of imports, blue bars, and exports, red bars, and increased trade with Central and Southern Asian neighbors up to 2038. Tajikistan and Kyrgyzstan have surplus hydro generation in the wet seasons, and they import gas power from Kazakhstan and Uzbekistan in the dry seasons, in the winter seasons. Next slide. With the introduction of renewable energy resources, curtailment is inevitable. Curtailment, the gray bars, is not a bad thing, as the energy cost from renewable energy generation is close to zero, and surplus renewable energy is required to take into account extended bad weather periods, the capacity factors of wind and solar, and the normal diurnal renewable energy patterns Example, the sun does not shine at night. Of note, in the left of the figure are the high unserved energy bars at the commencement of the study, the orange and blue, which were rapidly improved with the injection of new thermal energy storage and renewable generation capacity in the study. Next slide, please. For power systems to operate effectively, sufficient spinning reserve is required. This figure shows the improvement in spinning reserves from roughly 3% at the commencement of the study to close to 17% on completion of the study period. This spinning reserve is made up from imports, gas turbines, batteries, the largest contributor, and some hydro generation. Next slide, please. This figure shows a typical 3-day generation dispatch capacity profile in megawatts in the study horizon. So you can see that the demand was chronological and undertaken on an hourly basis. Of note is the gold PV comprising large daytime capacity, wind and hydro complementing the solar in the evenings, the blue, and batteries used at peak times, the dark green. The gas generation can be seen to provide the base generation requirement. The red dotted line shows the price of electricity increasing at times of system peak. Next slide, please. As mentioned, large capital spend on new generation assets, blue bars, required at the commencement of the study horizon for the following reason: to improve unserved energy, to replace old, inefficient generation with more efficient, reliable, and flexible plant, and the decrease in energy tariffs by the introduction of low-cost RE generation. The green line shows the cumulative capacity increase over the study horizon. A steep cumulative capacity increase is required at the beginning of the study horizon, and it can be seen to taper off towards the end of the study horizon. Next slide, please. Transmission analysis was undertaken over the study horizon to incorporate increases in load and new thermal, hydro, renewable and storage assets, and increased imports. The figure shows a schematic representation of the transmission system at the commencement of the study in 2018. The red lines are 500 kV transmission lines, and the black lines are the 220 kV assets. Square blocks show the power stations, and the circles show the substations. Dig silent power system analysis was undertaken for different study years, incorporating the new demand and the new generation, and static and dynamic studies were undertaken for normal N-0 and emergency N-1 system conditions. Studies were also undertaken for different times of the day, example noon, system peak, system minimum, etc. Next slide, please. The figure shows the final transmission system in 2038. Proposed 500 kV and 220 kV assets are shown as dotted lines. In some areas, large increments of wind and solar were required, and a lot of transmission infrastructure was required. Next slide. Further interesting findings in the study we undertook are as follows. As Uzbekistan increases its penetration of renewable energy, its internal requirement for flexible generation or energy storage will increase. it was recommended that whilst Uzbekistan should trade with its neighbors, its dependence on primary or FCR reserve from Russia should be reduced, and it should become energy and capacity independent. It was recommended that power plants should run in speed control or governing mode, and that ADS, AGC systems should be implemented. The ADS, AGC system should work in conjunction with an area control error, ACE system, as shown in the following slides. Large ramping and flexible generation and energy storage reserves are required, and climate change and system resilience factors should be introduced into the planning. Example, reduced glacial hydroflows and changing rainfall and precipitation patterns. Next slide, please. Some possible lessons for Thailand are as follows. Conduct regular country and regional IRRPs, integrated resource and resilience plans, possibly every 2 years, using the tools described in the courses, example PyPSA and DigSilent. Individual country reserves can be reduced via more interconnected systems. Regional interconnectors also provide generation source diversity due to weather and resilience to extreme weather events. ADS, AGC, and ACE systems should be introduced. Flexible generation and energy storage should be introduced as the penetration of renewable inverter-based generation increases. And if the penetration of renewable increases steadily, the introduction of synchronous condensers, which can then supply inertia, fault level, and dynamic reactive power response. Next slide, please. I'd like to move on to Barbados. We also did an integrated resource and resilience plan for this country. It can be seen there in the slide as a small island, 30 kilometers by 20 kilometers roughly, and it's in the Caribbean belt, just north of South America and to the southeast of North America. Next slide, please. So Barbados is a geographical and electrical island. It is not interconnected with other islands and lands. Barbados is totally responsible for managing its energy balance, that is, matching generation with demand. Barbados's power utility is privately owned and managed, and the company is called the Barbados Light and Power Company, BLPC. At the time of the study, BLPC was 100% reliant on imported diesel and heavy fuel oil, HFO, fuels for power generation. The other half of Barbados's power balance comprised fuels for transport and shipping, but this half of the power balance was not part of our study. The Barbados government promulgated the 2030 energy policy with the aim of decarbonizing Barbados's electricity. Beyond the 2030 energy policy, the government set a target to decarbonize electricity by 2030 and to introduce a designated percentage of electric vehicles, EVs, by 2030. We were commissioned to undertake an IRRP, Integrated Resource and Resilience Plan, for Barbados, and we undertook a demand forecast, a best cost generation plan, and a transmission plan for 2030. Notice I used the word best cost and not least cost. That will be explained later. Next slide, please. So the figure shows the energy balance at the time of the study. Of note is that more than 50% of electrical energy is lost due to the inherent efficiencies of thermal power plants. That's the green in the top right-hand figure. More than 50%, approaching 60% of electrical energy is lost as losses because power plants, thermal power plants, only have an efficiency between 30 and 40%. Electrical generation and transport comprise most of the energy balance demand, with the industrial oil demand comprising the next biggest. So you can see transport on the bottom in blue, bottom right on blue, and you can see industrial oil usage in the brown above the transport. Next slide, please. A demand forecast was undertaken to 2040. Of note in the diagram is the negative demand from demand-side management savings. Also of note is a significant growth in EVs, electric vehicles, to 2040, the gray bars. Residential demand decreases, and this is likely due to behind-the-meter PV and battery storage systems. And as mentioned, although this slide shows the demands as average demands for the years, chronological demand was formulated for each hour of the year for the 20-year duration. Next slide, please. For the generation planning study, 3 scenarios were studied. These were the least cost or no carbon scenario, the least cost carbon price included scenario, and the least cost but with forced use of local indigenous biomass. Next slide, please. Although the demand forecast was undertaken to 2040, the generation planning study was done to 2030. The figure shows the planned candidate megawatt capacity options to 2030. Of note is the large step increase in battery energy storage, the dark blue bars at the bottom, solar, yellow bars, wind, turquoise bars at the top, and even concentrated solar power, CSP, small gold bars at the top under the wind. HFO and diesel plants decline, the black and dark gray, but capacity remains for flexibility and dispatchability. Behind the meter solar rooftop is assumed to increase, shown in red. Next slide, please. The forecasted energy picture in megawatt hours shows a dramatic decrease in HFO and diesel thermal plants, with a corresponding large increase in renewable energy. Of note is the positive and negative contribution to energy from the batteries, the purple bars at the bottom. This is because batteries need energy to charge and provide energy when discharging. Next slide, please. The left-hand figure shows the weekly generation dispatch profiles at the commencement of the study, with HFO and diesel in black dominating the dispatch. The right-hand figures show the least cost or best cost dispatch and forced biomass renewables dispatch for 2030. So the top right-hand figure is the least cost, and the bottom right-hand figure was the least cost or best cost with biomass forced, a certain percentage of biomass forced. Notice the large contribution of solar, wind, and batteries, and the drop in importance of HFO and diesel. Next slide, please. As a result of additional generation, the unserved energy drops significantly over the 10-year study period for all 3 study scenarios. Next slide. This figure shows the cumulative capacity additions over the 10-year study period. Notice the decommissioning of HFO under the line and diesel plants, the negative numbers, and the large battery on the top left, solar in the middle on the top, and the wind on the right. Next slide, please. This slide shows a schematic representation or system single line diagram of the transmission grid and the power grid. Thermal, wind, and solar generation is dispersed across the system, even if renewable resources are not necessarily the highest in these areas. Energy storage is also dispersed across the system, which provides weather impact protection, but also deloads the transmission system in many cases, as excess renewable generation can charge localized battery systems instead of charging remote battery systems and overloading the transmission networks. By placing the renewable generation close to the loads, this also decreased the requirement for excessive new transmission assets and also decreased transmission losses. Synchronous condensers, SCOs, are placed at decommissioned synchronous thermal power plants to provide inertia, fault level, and dynamic voltage and reactive power support. Batteries from electric vehicles can be used for ancillary services, specifically for frequency support and even black start under certain conditions. Electric vehicle loads tend to be dispersed by their nature. Clearly, utility scale battery storage also works in conjunction with the electric vehicle battery storage. This schematic SLD evolves to 2030 as the system demand and generation change. Next slide, please. As Barbados is in the Caribbean and in the hurricane belt, it is prone to severe storms and infrastructure damage. One way of improving system resilience is to divide the island into electrical sub-islands, as shown in the figure. So if a storm damages assets on the right-hand side of the figure, those red circuit breakers, those bold red circuit breakers can be opened, and the 2 left-hand islands can operate while the right-hand island is restored and then can be resynchronized using resynchronization relays between the islands. The load and the generation in the decided islands should be matched so that the islands can operate effectively. Next slide, please. I'm not sure of my time, Tristan, but I'll carry on until I'm asked to stop.
Yeah, you have another 3-4 minutes.
Okay, thank you. So one of the things I said at the beginning was least cost and best cost. And Barbados exhibited some quite interesting non-technical aspects. So besides the technical cost and resilience criteria used in the IRRP, other less quantitative criteria or qualitative criteria were also used to evaluate the 3 main study scenarios. For example, because Barbados is a small island, roughly 30 kilometers by 20 kilometers, land is scarce, and there are competing uses for land, such as agriculture, residential, commercial, tourism, and electricity generation. Whilst the IRRP recommended large increments of solar PV, this energy source would require large tracts of land. Similarly, Barbados does not have mountains or large rivers, so water is only available from scarce underground aquifers. Some generation scenarios enabled higher levels of employment. Example, the local biomass option for the planting, harvesting, and processing of biomass. However, for this option, the planting of biomass crops competed with agricultural crops for food. The generation scenarios with the highest wind increments would have the highest visual pollution impact, and thermal projects would have other biophysical impacts. Some scenarios were more at risk of extreme climate than others. Next slide. A spreadsheet matrix was formulated which calculated the importance of an individual criterion impact from 1 to 10 and the extent that the scenario impinged on that criterion. From this spreadsheet, a total multi-criteria impact of each scenario, including cost, was formulated. Scenario net present value or cost was also a criterion in the overall multi-criteria assessment to be evaluated in conjunction with other criteria. A sensitivity analysis was undertaken on the weightings in the multi-criteria spreadsheet, and scenarios which consistently scored the highest were considered to be the best scenarios or the most robust scenarios on a wide range of criteria. And spider diagrams were formulated to show the results of the individual criteria for the different sensitivities. Thank you. That's the end of my presentation.
Thank you very much, Mr. Paul Tusen, for the excellent presentation of the two case studies that are totally different kinds. So the Uzbekistan is the one with land interconnection, and while the Barbados is not, but it has an aggressive plan, right, to achieve the 100% renewable energy and to become a carbon neutral island. Okay, so for the audience, if you have any question, you can keep your question and we can ask at the end of the seminar, or you can type in the chat box. Yeah. Okay, thanks again, Mr. Paul Tusen. So now we will move to the next presentation. The next speaker is Miss Ipileng Mokadinen. Sorry if I don't pronounce correctly. She's also from Data Tech, and she will present the topic renewable energy zones, the importance of cross-cutting decision support. Okay, Ipileng, please.
Okay.
Yep.
Okay. Sorry. All right. Good afternoon, everyone. Thank you so much, Dr. Sunarat, for the introduction. My name is Ipileng Mokadinen. I am an energy sector principal at Tetra Tech. As my colleague Paul has taken us through the various case studies where energy system planning was undertaken through various transmission and generation planning tools, I will be presenting to you the importance of cross-cutting decision making to identify and develop renewable energy zone as part of the energy system planning. Firstly, let me thank the USAID and KMUTT for the privilege afforded to me to speak to you this day. So just to kick off on this topic, I would like to highlight the fact that a lot of us, we are aware that we are living in a time where we are noticing an enhanced drive globally towards decarbonization and net zero goals from many countries. And consequently, we are seeing there's an increase of renewable energy developments to meet carbon neutrality goals across. So one way to achieve these clean energy goals in a timely manner is through this RE zones approach. So this approach of developing renewable energy zones is international best practice for development of utility scale renewable energy plants. It is recommended as it can achieve optimized, cost-effective, large-scale development, especially in countries that are still in early stages of renewable energy development. It is a multi-criteria and multi-phase methodology, and is used for identifying and developing predominantly solar and wind zones, but it can be explored for other technologies that are found concentrated in various geographical areas. So renewable energy zones can be defined as geographical areas that has high quality renewable energy resource, where large-scale renewable energy projects can be developed using economic scales of economic. So what are objectives in developing this renewable energy zones? So this planning can assist policymakers to ensure that their infrastructure investments can achieve national goals in the most economical manner. As we are aware, most of the renewable energy investors and developers are primarily interested in minimizing their costs and maximizing their revenue without much consideration for the cost of things like grid integration and any costs associated with social and environmental impacts mitigation that will be needed. So therefore, by undertaking this step in planning this renewable energy zones, it strikes a balance by maximizing the investor's return on investment, whilst also minimizing, ensuring that we're getting the best return, because we will be getting the most optimal renewable energy resource. So this holistic approach is effective in minimizing CAPEX and OPEX costs for the renewable energy integration by ensuring good resource quality in terms of renewable energy, and also ensuring that the transmission or the distribution network has available capacity to host these capacities. In turn, we get to lower the procurement costs and reduce associated integration costs. We also, it allows us to also define in advance the social and environmental impacts. And by doing that, consequently, we are shortening the period that it normally would take for the developers to acquire permits and approval of licenses. By doing this, we'll be de-risking these projects development, which in turn attracts capital investment, and it also allows the countries to design their own renewable energy procurement process that is tailored for their needs. In the next slides, we'll go through various criteria which we can employ that can assist us in identifying and excluding areas within the boundaries of application where development of these plants is not possible or prohibited for technical, economical, environmental, or other reasons. So the first criteria we're going to be looking at is the renewable energy resource. This criteria allows us to identify areas or zones with abundant renewable energy resource that is technically developable. We can use renewable energy intensity, resource intensity maps to identify these high resource areas. These maps will allow us to estimate achievable installed capacity and generation of specific technology based on topographic limitations, land use constraints, and system performance. So on this slide, we're seeing that two maps for Thailand. One showing, this one showing basically the solar resource in Thailand. So this map uses, it's found from Global Solar Atlas, and we can see that it uses the measurement of PV out as a measure of the solar resource. So PV out is a measure of the solar resource density expressed in kilowatt hour of electricity that will be generated by a PV system with 1 kilowatt peak installed capacity. So the PV out is the average annual plant output in AC, and it's inclusive of the AC and DC conversion efficiency and other losses. We generally accept a good PV out resource when it's around about 1,460 kilowatt hour per kilowatt peak. So as you can see for Thailand, this area, it's from this solar resource map, we can see there's a legend here showing this 1,460 or greater. It's this orange going to red. So you can see from this map found on this Global Solar Atlas where the good PV resource is at. For wind, we normally use the Global Wind Atlas, which is used to extract the parameter. The one that's shown here, it's displaying the capacity factor across Thailand. So this resource intensity map is converted to a continuous color ramp to highlight the high resource areas. So you'll see using the legend, the lowest ones are the light blue going all the way up. As you can see in Thailand, we see good resources along this area of Thailand. So, but also additionally, as much as we look at capacity factor, we should also in parallel look at maps that also show us the wind speed, just to inform us how gusty the wind can be in those particulars of interest. As the second criteria, we normally look at elevation and slope in those areas of interest. What elevation informs us on is that higher elevation makes it difficult to access the terrain. Slope is the measure of change of elevation along a horizontal distance. Zero slope means flat terrain, which is what we prefer when we are developing these renewable energy plants, as higher elevation makes it difficult to access. And also a higher slope will imply higher construction costs, which is something that we don't want. So as just what we normally look at, we prefer for wind average slope of less than 17 degrees and for solar average slope of less than 10 degrees. The third criteria we look at is the criteria of distance to the nearest grid. This criteria is incorporated in this planning process and used to it's used as a cost indicator. It helps us to plan, to approve, and build needed transmission or distribution infrastructure needed to access these areas and connect these high quality resources. In order for us to do that, I'm sorry, I'd like to switch off this. Okay. In order to do that, we normally have to do grid integration studies, which for that we normally will also have to do use tools such as Dixieland Power Factory, ETAP, and PSSE in order to assess the impact of these connections. And the outputs and recommendation based on those studies will tell us the needed upgrades and expansions and associated costs that will come with the connection of these plants. And by also doing these studies well in advance, it helps us to reduce the construction times, especially in the transmission network, as we know that depending on the length of the line, it can take time to do all the pre-engineering studies to construct these lines, as a lot of studies go also in parallel with that, as acquiring servitudes and all of that. The fourth criteria we look at, it's also a criteria done in effort to assess the costs associated with upgrades to existing roads, bridges, and tunnels, which we would need to transport equipment to these various zones. From this assessment, we can get an estimate of the length of new roads, and that way we are able to budget and look at the zones which are more cost effective to deploy and develop these RE zones. The fifth criteria, it's a detailed GIS analysis where we attempt to rule out areas which are environmentally sensitive, or they are protected areas, as our RE zones should not overlap with any of these areas. So these protected areas are normally defined in countries, and they can also be found on resources and sources such as the World Database on Protected Areas, key biodiversity areas, and important bird diversity areas. So these boundaries or areas are normally found in as layers in various GIS tools. By also defining or identifying these renewable energy zones, it allows countries to conduct their environmental and social impact assessments well in advance, so that mitigation costs can sort of be estimated. The sixth criteria we normally look at is the land use and land cover. Again, the renewable energy zones ideally should not overlap with built-up areas with water bodies. And other countries can define specific land use designations which we should not overlap with, for instance, agricultural areas and forest and flooded areas. PV zones ideally should also not be developed in areas that can be easily shaded, as this will affect your energy output of the plants. So we use the levelized cost of energy to rank our renewable energy zones. At this stage, we would have estimated the costs of all the criteria I've mentioned. You would have an idea of the energy yield that you can get from the various renewable energy zones. And at this stage, this criteria we are able to estimate, because at this stage it will not be actual costs, but we can estimate and rank the various renewable energy zones based on their levelized cost of energy. As we know, the renewable energy sites with the lower levelized cost of energy will be ranked higher. The total costs, the operational expenses, and energy yield for installed capacity of both the wind and the solar plants in the various renewable energy zones will be different, while the assumed financial parameters will stay the same. In order to use these zonal parameters in the financial model, the capital expense will be split into two components: the location-specific costs and the location-independent costs. Once we have ranked the RE zones based on their levelized cost of energy, different countries can choose to include other criteria to rank these renewable energy zones. For example, if they were to use geographic dispersion as a criteria, this would mean that even though the levelized cost of energy in that zone is not necessarily the lowest, but because of the country is interested in offering resiliency to their network, this zone can be selected. Or even in other criteria, for the fact that the renewable energy zone is close to load centers, they can choose to include it and rank it based on the proximity to the load centers, because that will mean that the generation will be closer to the load, meaning less technical losses. Again, this could also mean that it's an opportunity for job creation and local participation in those areas. However, I would like to add that oftentimes also the developments of these large-scale renewable energy plants can cause communities to be resistive because of issues to do with noise concern, land use conflicts, and visual amenity impacts. These can be seen as challenges. However, if we define these renewable energy zones well in advance, we can create opportunities in these challenges. The opportunities can include things like involving the communities well in advance and allow them to be involved in this planning process by offering opportunities such as direct payments to the farmers for hosting wind and solar, these solar plants, allowing them to lease their lands for these developments. We can introduce direct and indirect jobs by ensuring that local contractors are part of the procurement of local goods and services. And the government can also include in their auction mandatory rules, such as developers subcontracting portions of their contract to the local people. These opportunities can also include socioeconomic benefits, whereby there will be an opportunity for those developers. You can enforce them to build roads, to build schools, for the community, or create even trust funds. And other benefits could be the agri PV, where we allow the farmers to herds to graze where these solar panels maybe are at, as examples of the opportunities that can be created by defining these RE zones well in advance, so that you mitigate resistance from communities. So the roadmap to developing these renewable energy zones, this is a typical flow chart used by the International Renewable Energy Agency ARENA, which they used for a specific project. But this is to highlight and confirm that they used like a similar approach in developing these renewable energy zones. As you can see, there's the resource assessment where because now they've identified these zones, they're able to size how they will be broken down into various land parcels. What is the size in megawatt that each and every plant is to have? But to summarize this this flow chart, it basically, the roadmap is that we have to perform desktop studies to preliminary identify these RE zones, and we can use GIS tools as those solar resource map and wind atlas. We can estimate all the costs associated with construction based on the elevation that that particular zone is, and there's cost implications to every criteria that we have discussed. And once we've calculated the levelized cost of energy for these various zones, we can rank them. And it's at this stage it's important to note that the levelized cost of energy will be a high level calculation. And as mentioned, you can rank them also on additional criteria that the government can introduce. After we've identified and selected our RE zones, it's good practice to do site visits and to start on the on-site measurements for the renewable energy zones, because remember, you would have gotten your resource data from satellite weather data. However, it's good to deploy also at least for a good practice is to at least put up MetMasts or parameters in these identified zones for at least 1 year, so that your developers can have accurate weather data, which will, because you're giving them sort of accurate data, it de-risks the projects, and then you can move to the last stage of developing these RE zones. So in conclusion, the renewable energy zone planning approach can assist policymakers and planners in meeting their clean energy goals and meet their increased demand by providing economic power generation through successful integration of utility scale deployment of renewable energy plants. The benefits of this, as mentioned, it will enable us to develop a country-specific roadmap, which is tailored to target national energy goals, policies, and we can choose the tailored scenarios. It allows governments and stakeholders to identify and reserve these land areas proactively, to get them environmentally approved, to ensure that when investors and developers come to play, there's already pre-approved licenses and land permits, which will lessen the time taken and allow countries to meet their goals in good timing. As mentioned, on-site data measurements allows developers to use real data to estimate the renewable energy source in their financial models, which will help decrease the tariff, the procurement tariff that they can give you. We can also be able to decrease grid interconnection costs, as these multiple projects can share the costs of developing these transmission infrastructures, and it allows the country to specify their procurement design and the social economic benefits they would like to achieve through the developments of these renewable energy zones. That is my presentation. Thank you very much.
Thank you very much, Ipaleng, for the comprehensive presentation on how the RE zones can benefit the design of the energy system. And okay, so I think because we have some time before the schedule to break, so maybe we can allow some question for these two presentations before we go to break at 2:20. So if you have any questions for the Mr. Paul Thussen or Ms. Ipaleng Mokadien, you can raise your hand and ask the question as well. But may I start with some, actually it's not the question, but about the IRRP that maybe Paul has mentioned about. Could you elaborate a little bit about the IRRP, and when you said that the IRRP recommended the solar PV for some of the model, I cannot remember which case, but so just want to know what IRRP is, and also what is the kind of criteria that give some such recommendation.
Yeah, I don't know if Tristan's got some slides, some IRRP slides available, but historically, IRP, which is an integrated resource plan, looked at technical and financial criteria. So will the plant work? Does it meet the demand? Is it dispatchable? And is it least cost? So that's traditionally how IRRPs have been undertaken. The problem with that approach is that the world has now changed. It has changed, it is changing, and it is going to carry on changing. So where there was a river before that had predictable, known water flows, that river no longer has any water in it. And if you want me to give you some real examples, I can give you 3 or 4 without even trying to think. Some rivers have completely dried up. Some rivers are going to dry up in the next 10 years. And some places where there never were rivers, there now are rivers. So that is an example of resilience planning. That's the third R, or the second R, IRRP, is the integrated resource and resilience planning. Historically, nuclear plants were placed close to the sea so that they could get cheap, low-cost cooling. Now, with rising sea levels and with storms and with tsunamis, maybe that needs to be rethought. So if you're going to be designing and building a nuclear plant, you need to take into account maybe not the least cost siting for that nuclear plant, but you need to take into account weather criteria. Transmission transformers, transmission lines. Traditionally, you template the lines. Templating means the sag of the lines at certain temperatures. So you template or you design the sag of your lines for certain ambient temperatures, and they should be okay for high load situations and high ambient temperature situations. Now temperatures are changing. Temperatures in some places have gone up by 2 to even 5 degrees Celsius. I'm not saying that that's the average global increase, but localized temperatures can go up as much as 2 to 5 degrees. Now your templating criteria for your lines have changed, and your transformers are now overloading because the ambient temperature has increased. So you need to design your plants with bigger transformers. You have to template your lines, your transmission lines at less cost-effective temperatures, etc. So the whole aspect of deterministic design and planning now needs to move towards deterministic and probabilistic planning and design, and that's where that second R comes in. So I hope that gives you. I can talk for a long time on this, but I think maybe that gives you a flavor of your question. Does that answer your question?
Yes, I think, yeah, I understand more about that. Yeah, and another short question is on the when you do the cost analysis, like least cost, is it based on the current price? Is also include the price inflation?
Yes, that's a good question. So often when we do these studies, we use real costs. Okay, so we exclude the inflation, and the discount rate that we use is a real discount rate, not a nominal discount rate. So that makes the calculations a little bit easier because you don't have to worry too much about inflation. There is, outside of inflation, there is a function called escalation, which is outside of inflation. That is just the fact that aluminium is becoming more expensive because it's more expensive to mine or produce. So that's an escalation impact, but that's outside of inflation. Okay. Your question was just repeat your question.
Yeah,
There's
about
one more point that I want to make. Sorry.
I just asked about the price, whether you use
price cost. Yes. Sorry. I wanted to just answer the second part. Now, as you know, the renewable solar PV costs are coming down all the time. Wind costs are coming down all the time, although I want to just modify that because wind sites can get more difficult to obtain. So you might need to go offshore wind, and you might even need to look at floating offshore wind, which is more expensive than land-based wind. But in general, costs are coming down. And as you know, battery costs are coming down all the time. And there are new battery technologies. So when we do these 10 and 20-year planning models, we put in what we call learning curves or cost curves. So we won't just have today's cost for solar, we'll have the cost as they go down. Real costs, the real, not the nominal, real cost goes down over the next 20 years. The wind costs, the battery costs go down. So yes, these generations least cost or best cost simulation packages do allow you to put future costs in, and obviously your demand is also changing. So you need to put your future demands in the planning model as well.
Okay, thank you very much, Paul. So now it's 2:20, so it's time for the break. We will have 10 minutes break. So see you again at 2:30. Yeah, and any other question, please ask at the end of the webinar. Thank you. See you then.
discussed and mapped out so that key financial decisions can take place, and so that feasibility of the infrastructure has been assessed so that
Good afternoon. Welcome back to the webinar series 2, Power System Optimization for Capacity Expansion Planning and Sector Coupling with PyPSA Case Study and Demonstration. The third presentation for today is on the topic Power System Optimization, the future of Gotham City's power system. And the presentation will be delivered by Mr. Tristan Kusis from Tetra Tech. Hi, Tristan. The next 30 minutes is yours.
Thank you, Dr. Sunarat. I hope everyone can see my screen.
Yep.
Yeah, thank you for having me today. It's a pleasure to speak with my colleagues, and I hope that what we cover today will be useful and give you a greater understanding of this topic of power system optimization and capacity expansion. Now, Paul started off our session today by looking at some case studies that had been undertaken in the past few years, looking at 2 different types of countries and the process that's involved in conducting these studies. And then Ipileng took us through an assessment of what's the process that's involved in introducing new generation into the system in the form of renewables. What are the best practices that we are seeing in use today? Now, what I'm going to speak about now is one of the tools that is being used across the world, from researchers to private entities to government institutions. And that is this tool called PyPSA, or Python for Power Systems Analysis. So I'm going to do a quick recap of what we covered in the previous webinar, speak about why do we need PyPSA, why is it important, why are these types of tools important, how does it work, how do we use it, and then just give a fictional case study of a system called Gotham City. So, all right, let's get started. What is PyPSA? Well, Python is a tool called Python for Power Systems Analysis. So it's a free and open source tool used for simulating and optimizing multiple electrical power systems over multiple periods. Okay, so what does that mean? Well, we have our power system that currently exists. We need to understand how it functions on a day-to-day basis, how much it costs. We need to look forward to the future and plan how to expand it, understand what retirements of current systems, current generators on the systems mean going forward. We need to understand how we satisfy existing and future demand of our power system. And we need to make sure that we do this in a least cost way. So fortunately, we can make use of the power of optimization. And what is that? It is essentially finding the most optimal set of decisions going into the future for selecting different generation technologies and expansion of our power system. What do we mean by least cost or optimal? Well, it's as in the word that Paul mentioned, it's always looking at least cost, but we also are now looking at best cost. So what else does PyPSA include? Well, firstly, it includes all of the conventional power system generation technologies that you would know. It includes the ability to look at unit commitment of your power system. And more importantly today, it includes the ability to model variable renewable generation, storage units, as well as coupling to other energy sectors. And I believe Dr. Natapong is going to touch on sector coupling in his session. On top of that, it has the added benefit of the ability to simulate mixed and alternating direct current networks. So it's not just looking at your generation and demand, it's looking at the transmission and potentially distribution system that connects all of this together, and some of the other interactions that we can't forget about in our energy system. It's not just electricity, as you can see in this figure over here. So what else do we know about Python? Well, it's designed to be easily extensible, to scale well with large networks and long time series. For example, if we're looking at Barbados, it's a very small system, yes, but we still need to look out to the future. We need to look out a week ahead, a month ahead, a year ahead, potentially decades. On the other side, we may be looking at a larger country or a group of countries, as you can see on the right-hand side here. This is looking at the European power system. So this tool is particularly well suited for looking at these types of systems, analyzing them, assisting in the expansion of these power systems into the future, and potentially understanding how we should operate them in this least cost way. Something else about the tool, it allows for the formulation of the full power flow equations, multi-period optimization of operation and investment with linear power flow equations. So what does that mean? Well, as a power systems specialist, you may want to look at how the power system operates when running load flow. Do you have the right capacity for your transmission lines, for your substations? Is the power getting to where it needs to go? And is the correct size is the correct amount being generated from certain regions? So looking from a power systems perspective, but also on the other side, from an economic perspective, are we making the right investment decisions? And how are we running the power system today to ensure that it's running in a least cost manner? So where does PyPSA sit in the group of tools that people might know about? On the left, we have PSSE, Digslint, ETAP. These are your traditional power systems study tools. On the right, we have, for example, Plexos times osmosis, and these are your economic tools for assessing power systems. Now, PyPSA sits in between these two groups. It has the ability to understand a power system from looking at load flows, nonlinear load flows. On the other side, we can look at the economic dispatch and the expansion of the power system. Now, when we use these tools, we can't just look at it in isolation. We know that we have information coming from very many different sources. We need to be looking at the cost of technology today, the cost of technology going into the future. As Paul was mentioning a little bit earlier, we need to understand the differences between certain technologies and how they may be implemented and integrated into the power system. So these technology costs are very important to model when we are looking to understand this least cost optimization going forward. On the other side, we also need to think about what Ipiling mentioned about the renewable resources that we're going to be tapping into when we're moving forward with a higher penetration of solar PV and wind. Understanding the wind speed and the level of irradiance in certain areas of your country is very important to get an understanding of the amount of energy you can expect from plants, the capacity that you can expect from a certain installed capacity of plant on a day-to-day, month-to-month, year-to-year basis. So all of this information comes together with PyPSA and allows us to model our complete power system. Now, PyPSA, as you probably heard in the name, has got Python within it. So it's actually based on Python. You will need an understanding of Python to create these models, run these simulations, And there's a number of tools that assist in this process, from installing the Python programming language to looking at the source code of the PyPSA tool, editing tools, understanding the different packages involved. This is all of these tools assist in undertaking these studies. So why are we here again today? Well, there are some challenges that we know about, and some of these challenges are coming about firstly because we understand that climate change is becoming more and more important. A number of countries have introduced nationally determined contributions to reduce the use of fossil fuels. And as you can see, in the past, we've made use of a lot of these fossil fuels to run our power systems. We had thermal and hydro generation technologies that were dispatchable. They were built in time to accommodate growing load. We had electrical demand that was somewhat predictable. And as this generation reached its retirement, we just built another generator in its place. So it was a little bit more predictable than what we are looking at today. So, all right, let's move over to today. We're seeing there's an increasing electrification of all energy use cases. So one of the biggest examples today is electric vehicles. Some of the thermal generation technologies used in the past are now no longer, we were no longer able to install them. And for multiple reasons, they're detrimental to the environment. But on top of this, we have limited resources of these fossil fuels. So we need to find a way to use these renewable energy technologies and integrate them into our grid. On top of that, as we had in the past, this older generation is reaching retirement. And in some countries, there's a lot of this generation that's reaching retirement, potentially forced retirements to comply with some of these climate commitment goals. So we've got to introduce these new clean variable generation energy storage technologies, and the grid needs to satisfy all of these needs. So why are we using PyPSA? Well, as engineers, we need a tool to model the interactions between the electrical grid, the consumers, and the generators. And most importantly, it is ensuring this triangle at the bottom, that we have sustainability, reliability, and affordability. So in the past, we had very predictable power systems. We'd planned for it for many decades. Now in the future, we have a more unpredictable system, and we need to understand the stochasticity of our generation sources going forward. And some of the challenges on the left here that we also covered in the last webinar. So what are these sustainability, reliability, and affordability criteria? Going forward, we need to respect environmental constraints, from greenhouse gas emissions to preservation of wildlife. Ipileng touched on this when looking at these RE zones, ensuring that we have the least impact on the environment as possible, not only avoiding protected areas, but we also need to look at the social and political constraints that we have, particularly looking at cities as an example. When cities become very built up, it's difficult to ensure that they have power. And the main ways of introducing power into large cities is a transmission system. So there has to be a give and take between the public and utility and government. On top of that, there has been some pushback by some communities in introducing generation technologies. Sometimes it's from offshore wind, sometimes it's from nuclear power. So there's not just we need to understand that it's not just a cost decision here. It's not just the economics that's involved. It's a multifaceted problem. Looking over on the reliability side, we need to ensure that all of our customers have reliable and secure electricity or energy, whether it's coming into their homes, their businesses. And we need to ensure that when the wind isn't blowing, when the sun isn't shining, that this power is still delivered, and even when components fail. So this is the next criteria that we discussed. Now, this is somewhat linked to Paul's discussion on resilience as well. And lastly, we have affordability. We need to ensure that the system is least cost so that we can pass that on to customers. We need to ensure that the cost of electricity is affordable for the population. So all of this information is fed into the modeling process, and some of this assessment takes place outside of PyPSA, but then you need to get onto the modeling and using PyPSA to create this optimized pathway. So how does PyPSA work? Well, it uses a partial equilibrium model that optimizes for both short-term operation as well as long-term investment. So we're interested on the hour-to-hour operation of our system, but we're also interested in the year-to-year, decade-to-decade investments, retirements, and changes to the power system. Some of you might know the partial equilibrium model is also known as a bottom-up model, as opposed to the top-down or general equilibrium. So PyPSA takes all of these constraints and it converts them into a linear problem by modeling the energy system using a set of linear power flow equations. So this is what we take our constraints and they convert it into these linear power flow equations and constraints. The tool minimizes total system costs by incorporating the fixed and variable costs of generation. So at the bottom over here, you can see that we are minimizing the yearly system costs, and that's made up of the annualized capital costs, so how much it costs to install generation, transmission, and any associated infrastructure. And that's all added up over the timeline of the investment horizon. But we also need to consider the marginal costs, and this is going to come in the form of variable and fixed operating costs. And what we are considering in this component for certain generation is the fuel. We're minimizing total system costs as well, not only on the generation, but on the storage, transmission, and distribution side. And we're looking at the technical, operational, and physical constraints, as well as some of the other constraints that I mentioned over here, by ensuring that we have a sustainable, reliable, and affordable system. So this is all condensed into this objective function. Now, this objective function shown over here gets a little bit more complicated when you drill down into it, because it breaks out all of the different generation and components and power system components that are used to fully construct the total cost. So we convert these technical, operational, and physical constraints into our set of linear equations, which is then mapped to this optimization problem. What are our optimization variables? Well, there's a number of degrees of freedom. There's a number of decisions that and possibilities that the power system can operate in at every given point in time. So an example over here is the power plant dispatch. There are also constraints that I mentioned before, physical constraints, and these are particularly due to the limits of some of the technologies in question. So for example, Paul mentioned that there are limits to how much power you can put through a certain type of transmission line. And then it is sent to the optimizer. So this feasible space is built by the solver, which is a multi-dimensional polyhedron, because we're looking at a multi-dimensional solution space over here with many different axes from all of the different constraints and options the solver can look at. And it uses one of two systems to solve the problem. either the simplex algorithm or the interior point algorithm. So I'm going to leave it up to the listeners to go and read more about these, how this process is undertaken. But really what we're interested in is the outcome. So this is where I'm going to transfer over to our example. So I'm not sure if anyone attending this webinar has heard of Gotham City. It's an interesting place that we have been told they have plans to decarbonize. So the mayor of the city has put a plan forward, a policy to decarbonize in the next 5 years. There's multiple reasons for this. One is that, as you can see, this city has struggled for years with pollution from a coal-fired power plant. As it's a very small island, the coal-fired power plant has to be located on the island somewhere, which is not great for the health of citizens. Their only other power source, unfortunately, is a hydropower plant. And the reason I say unfortunately is because it will not be sufficient to cater to the city's needs currently and as they're going to grow. Now, we have seen a recent reduction in costs of alternative renewable technologies. And on top of this, we have to think about this retirement of our coal-fired power plant. And we need to look forward to ensure we satisfy these criteria, the sustainability, reliability, and affordability criteria. In the study, we're going to look over the next 5 years. So this is a very fast change that Gotham City is going to have to undertake. There's a number of parameters that we're not going to consider for simplicity. We're not going to look at the CO2 emitted, although I'm pretty sure that the CO2 emitted after the coal-fired power plant is retired can be a lot less than before. We're not looking at the reserve margin on the power system at the moment. And there is this topic called energy transition mechanism. We're also not going to discuss this as it gets into a lot of detail on how exactly a country or a region undertakes the shift from using older generation technologies, fossil fuel power plants, to these new renewable technologies. Okay, so Gotham City currently has 3 substations: Wayne Manor, the Reservoir, and Clock Tower. City currently has, as we know, its coal-fired power plant of 200 megawatts and a hydro of 300 megawatts. This fellow by the name of Bruce Wayne has offered the use of his manor's lands for a solar PV array and a battery energy storage system. So you can see that to the northeast of Gotham City, which is located in Gotham County. Let's have a look at the network today. We have 3 substations, so 3 buses, and we have a transmission line connecting each of these 3 buses or substations to one another. We have our coal-fired power plant connected at Clock Tower, and we have our hydropower plant installed at the reservoir. What I'm illustrating here as well is the potential for new generation, or candidate generation. So at Wayne Manor, we know we have the potential to install some gas turbines. There is space. We know we may be able to install a solar PV plant and some batteries. There's a similar situation over at the reservoir: batteries, solar PV, and wind. And then at Clock Tower, we only have the possibility to install wind and a gas turbine. There's limited space down by Clock Tower. So what does the system look like today? Well, it's a lot of coal and it's a little bit of hydro. So currently it's able to meet the demand, and this is looking over the course of a week. So you can see your morning and evening peaks, and system is functioning. Going forward, however, we know that this area shaded in black is going to go away. So we need to change very quickly. Okay, so let's look at Gotham County, or Wayne Manor. Our potential technology options, we've got batteries, solar PV, and a gas-fired power plant in the form of an OCGT. And Bruce Wayne has told us that he has offered the use of his lands for this battery energy technology. He's told it that there is a land constraint or a space constraint for this technology. He's going to install it. It's going to be underground. We're not sure where. He has told us that it used the latest technology, so it's more efficient than other battery systems on the market. And he has also told us it's cheaper. We understand that he is assisting in the process of getting these batteries. He has offered the use of his estate grounds for the solar PV array, which is excellent because it's just outside of the city, and there'll be limited problems related to resettlement or finding enough space. So now let's move on to the reservoir. So the reservoir, we know we have our hydropower plant, and we have 3 other technology options. A quick look at the hydropower plant. Well, it has 30 years of remaining life, which is excellent. It's past the time horizon of our study, which is only 5 years. It has a lot of storage in it. So at full output, it can provide energy for 6 days, and it has 300 megawatts installed. What about our candidate technologies? We can install wind, although we've been told that it's a low capacity factor, which essentially means we may not get as much energy from a wind power plant installed over here as we would like. However, it's cheap because it can be on land. We can install solar PV, but there's limitations to that. And we can also install a battery energy storage system. It's not as cheap as if we were to install at Wayne Manor. And lastly, our substation at Clock Tower. So this is where we're going to be retiring our coal-fired power plant, and it's going to be retired in 2 years' time. It has an installed capacity of 200 megawatts, and we can install a gas turbine over here. And we also have the ability to install offshore wind. And we understand that with a number of studies that have been undertaken, that this offshore wind has a very high capacity factor. So over a given year, we will expect a large amount of energy from this plant. However, it's offshore. It's going to be more expensive than if we install at the reservoir. Okay, so let's put all of this information into the model. We need to combine this information with the demand. So as you can see here, we have our weekly profile, our morning and afternoon peaks, and it's a growing city. It's approximately 6% year-on-year growth, which is phenomenal. What this means, though, is we need to install enough capacity, enough new generation to cater for this existing and growing demand. All right, let's run the optimizer and see what happens. What can we understand from this? Well, the system chose to install a lot of this battery 1, and I suspect that it chose to install battery 1 because it was more efficient. So this has a 95% efficiency against battery 2, which is only 90%. It's cheaper. However, we can only install 500 megawatt hours. So what else did the optimizer tell us? Well, it said install 526 megawatt hours of this first battery, okay, which is very close to our limit over here. But the optimizer also said that with this 526 megawatt hours, it's still not enough to cater for the system. We still need a little bit of additional battery energy storage from our second plant, our second substation over here. And this is, even though it is more expensive and a little bit less efficient, it still makes sense to install batteries over here. So I installed about 113 megawatt hours. Okay, now let's look at the PV. So our PV array 1, we have a 27.2% capacity factor, which is excellent. That's a very high capacity factor. The use of the land over here means that we can extract a lot of energy from this plant. But now, if we compare the capacity factor from PV array 1 to PV array 2, we see a noticeable difference of about 10%. So the capacity factor of PV array 2 is quite a lot lower. And we believe that this is because the installation of a plant over here suffers from changes in elevation. So during some times of the day, it will be shaded because it's behind some rocky outcrops. So what does the optimizer tell us? Well, install more of PV array 1 than PV array 2. It still said install at both sites though. And finally, what about wind? Well, unfortunately, at our wind farm 1, we only have a 1.2% capacity factor, which is not great. However, it's lower cost, so it does have that going for it. What about if we compare it against wind farm 2? Well, this has a 19.6% capacity factor, which is much better. Again, it's expensive because it's offshore. What does optimization tell us? Well, it says only install at wind farm 2. What it's saying here is that wind farm 1 with 1.2% capacity factor just doesn't make economic sense to install. We will get almost no energy coming out of this plant for the installed capacity. We won't be able to recover the costs. And if you have this alternative wind farm 2, that's excellent. Okay, our hydroelectric power plant, that's going to continue operating. We've been told that there's a natural spring, so it's refilled by this natural inflow. And we can use it as a low-cost battery storage device because it has about 6 days worth of storage, which is excellent. And it's fortunately free. Okay, now let's have a look at the capacity. So in black over here, you can see the capacity of the coal-fired power plant. After that 2-year period, it goes out of service. So we've retired it. But now we need to install this additional capacity so that when this plant goes out of service, it will be a seamless transition. So you can see the installed capacity of these other generators on the system. Now you'll see a little bit of brown, the light and dark brown installed as well. So it's these little amounts of capacity installed. So let's see why that is there. And I think the best way to illustrate that is by looking at the energy sent out. So 2023 and 2024, a lot of our energy is coming from our coal. Going forward, it's going to change. When that retires, a lot of our energy is coming from our hydro, it's coming from our wind, it's coming from our PV, and also some of it is coming from a gas power plant. So it's to cater for some of these periods where there is low wind and low solar, where the hydro can't provide energy. So that's an interesting outcome. We can see that we have growing demand that's satisfied by the new generation coming online. And we are also looking at a system that is producing less CO2, less emissions into the atmosphere, which is great for people's health and great for the environment as a whole. Now, this example over here is very basic. We've ignored a lot of the parameters. We haven't looked at curtailment. We haven't looked at the energy transition mechanism, CO2, reserve margin, heat rates, learning curves, detailed demand projections and profiles. This is all of the type of work that is included in conducting these type of studies. And this is only for a single scenario as well. Unlike what Paul mentioned in his case studies, where there were a number of different scenarios for future pathways for the country. So this is our final picture of the system, of the installed capacity and the retirement that you can see down at the bottom. And it looks very different on a day-to-day basis from what we saw previously. We now have a lot of our power system operating on solar, wind, hydro, and where there is excess, it's being charged by batteries, and where there is a lack of renewable energy, it's being provided by the batteries and also by gas in certain periods. So it's a very different picture from what we've seen in the past. And this is the power of PyPSA. This is just one of the types of assessments that you can conduct using this tool. Thank you.
Okay, thank you, Mr. Tristan Crisis, for your comprehensive presentation on how PyPSA works and the outputs from the model. Yes, so now I would like to move to the final presentation today. The presentation will be given by Dr. Nattapong Chayawatto from KMUTT on the topic Energy System Optimization, the case for sector coupling. Dr. Nattapong, the next 30 minutes is yours.
Yes, can you see my slide?
Yes, yes, perfect.
Yes. Thank you very much, Ajahn Sunirat, for your introduction. And good morning and good afternoon, everyone. I'm going to present the topic sector couple engine system with PyPSA. This one is very important for the PyPSA. So this is the subtopic. I will make a presentation. I will start with a formalization of optimization modeling approach. In this slide is more or less the same with Tristan, just give you the presentation. And then I move to the what is sector couple engine system. I will talk about what is the meaning of the sector couple in terms of supply side and the demand side. And the last thing, I will show you the case study. I use case study from the PyPSA website. And actually, because of the time limitation, and that's why I select only 2 simple case study from the PyPSA website. So you can see the concept for the optimization is more or less the same with Tristan just presentation. PyPSA can optimize the dispatch of generation and storage unit, and also can optimize capacity of the generation, storage, and transmission infrastructure by using cost optimum. In terms of the cost optimum, we use the annualized capital cost and the marginal cost under the constraint, for example, to achieve the energy demand in each sector, and also the constraint of the transmission line, and also the constraint from the renewable energy, especially for the variability of time series, and also from the geographical potential. If you remember from the EPLIN presentation, we need such kind of the data from the EPLIN to include for the constraint for the optimization. And also it's a popular issue for the carbon neutrality, for the carbon limitation. It's one of the constraints. It can be included in the PyPSA. And also we can include the flexibility from the gas turbine, battery, hydrogen, or HVDC link into the one of the constraints for the PyPSA model based on the cost optimization. So I move to the meaning of the sector couple or the energy system. For the energy system, the PyPSA can add the demand and supply sector to the grids and storage. The example of the sector couple, for example, is a transport sector. We can include the EV to the energy system with the PyPSA, and also we can include the space and water heating in residential sector, or commercial sector to the PyPSA, and so we can add biomass or energy consumption in various sectors. For example, from the agriculture and the information for the consumption from industrial sector, and also for the carbon management, carbon capture and utilization, we can include in the PyPSA. And one thing is keep in mind, PyPSA cannot include for the waste management and agriculture, forestry, and land use and land cover. So you can see in the right hand side, this is very diagram to show the overview of the sector and the links. On the left hand side is show the supply side or source side, and the middle show the grid system and storage, and the right side show the demand side. We can see the link between source, grid, and storage and demand side. For example, for the wind and solar PV energy, it can generate electricity and go to the grid system, and the electricity can transmit to the demand side, for example, for the electric device, and also can go to the heater or the heat pump, and then go to the industrial sector here. And apart from the wind and solar PV, we can add the hydroelectricity or biogas or fossil gas and biomass. And one of interesting we call the atmosphere is represent the CO2 emission in the atmosphere. We can input the data for the CO2 emission, and so we can do the component we call the direct air capture. I will show you in my case study as well. And also we can input for the carbon capture. And yeah, this is the overall of the sector and the link for the sector couple using on the PyPSA. So I move to for my first case study I will show you. As I told you, I got this example from the PyPSA website. This is a simple case study. This case study is a battery electric vehicle aim to optimize the size of PV panel. We can see on the right hand side, we have the node we call the bus, or the place of the office, the place of works. And in this bus, there is a PV panel installation with a capital cost. For example, in this case, it's 1,000. And also in the office, they have the charger, and for the charging the EV. And in this case study, we have the assumption for the battery electric vehicle we call the BEV. And normally the driver use the BEV in the morning period for the 100 kilometer in the morning, and drive back to home in the evening for the 100 kilometer as well. This is like BEV uses for 2 times a day. And for the charging duration, can be get the electricity from the PV panel. We can see on the right hand side the PV panel installed at the place of work, or I call the office. And the last thing, the battery in the EV, the sizing is 100 kilowatt hour, and in the consumption of the battery is 0.18 kilowatt hour per kilometer. This is the data will be used for this case study. In this slide, it shows the input data. On the left hand side, it shows the petrol usage of the BEV. As I said, the battery will be used during for the driving from the home to the office in 2 times, in the morning and evening period. And after that, the battery will be charged during the daytime, starting from the 8 o'clock until 19 o'clock. So, and the right-hand side is available of the charging. The middle is show like the PV profile, and the right-hand side is show the availability of the charging. This is the input information we have to enter in the right. We have to write the script in the PyPSA. This is only the overall to give just the idea how can we do the modeling on the PyPSA. As we know, the PyPSA is based on the Python language. And on your left-hand side, we start with the import, the packages. One of the important packages we call the PyPSA. And also we have to import for the pandas or matplotlib. And then we have to input the information for the consumption pattern of the BEV. We can see in the time series only 1 day. In this case study, we assume it can be happen on the 2016 is 1st January. So after we input the pattern of the usage of the BEV, and then we have to input the PV profile in that day. And also we have to input the data for the charging period or charging availability. And on the right-hand side, we have to initiate for the network. We have to identify the bus we call the office. We have to identify the battery. And so we have to input the create, we call the PV panel. We call the create with we call the component is a generator, is a name, is a PV panel. And then we have to input the load. The load is mean like the pattern of the battery. So, and then we have to create the link. It's like it's name of the charger, and that's it for the data for in this case study. And then we run optimization. We just type the command for the optimization. But the thing we have to write the script based on the Python. So this is the result for this case study. As I said, for this case study, we do the optimization of the PV panel sizing. And the result, you can get the optimum panel sizing is about 7 kilowatt. And so we can see the operation for the energy output and the state of charge during the day. And we can see the blue color represent its energy output. You can see the energy output from battery for to drive the motor for the electric vehicle. It can generate. It can use in this time for the driving from home to the office, and also it's a 2 times a day. And so we can see the state of charge. And in this period, it's a discharge from the battery to the motor. And after go to the office, there will be the period of the charging from the PV panel. And for my presentation today, I do not analyze in detail, but I just give you the overall how can we do the modeling based on the PyPSA. So I moved to my last case study. This one I call the biomass synthetic fuels and carbon management. This one a little bit more complicated compared with the previous case study. But in this case study, it's aimed to manage different biomass stock. That means in this study, they have 2 biomass power plant. We try to compare which one should be like the cost optimization. with the different potential and cost, and the program will select based on the cost optimization, and also the component or the sector copying will include the fuel synthetic fuel production and direct air capture, DAC, and the carbon capture. The target in this case study try to achieve the net negative emission over the period. That means we try to achieve the CO2 reduction. For the assumption, the load, it can be for the electricity, it can be for the demand for the transport, and also we have the hydrogen production using the electrolysis process, and also there is a storage for the hydrogen. And also there is the diesel production from the hydrogen, and for the CO2 using the future stove and storage, we have the diesel storage after get the diesel production. And also in this case study, they have the CO2 emission to the atmosphere. And the last one, in this case study, we will call the DAC or direct air capture. For this component consume the electricity to take the CO2 from the air to the underground or the CCS. This is the assumption. So this is like the diagram for the overall of this case study is a little bit complicated. We can start from the left-hand side. We have the node for the transport, the demand from the transport, and we have the diesel car, and also we have the diesel production. The result from the diesel car, it can emit the CO2 carbon dioxide in the air, and then the output from the diesel car will go to the CO2 atmosphere, and also there we have the stove to get the data for the CO2 atmosphere. And also in this case study, we have the open cycle gas turbine with the CCS. We have the open cycle gas turbine without the CCS. And so we have, as I said, we have the direct air capture in order to capture the CO2 emission in the atmosphere into the CO2 store or the carbon capture. And also we have the feature scope for the diesel production. To do this, we need the input from the hydrogen production and the CO2 to do the process of the feature scope. And on the right-hand side, we have the node for the hydrogen production. We have the hydrogen storage. To get the hydrogen, we have to use the electrolysis process. That means we have to use the electricity to for the process of electrolysis. And so on the bottom, on the right-hand side, we have the electricity bus. And also, as I said, we have the biomass power plant. We have biomass power plant with the CCS is 1, and the biomass power plant with CCS 2. But for the 2 biomass power plant is different with the marginal cost and the number of the feedstock. And the software will do the calculation for the cost optimization. So this is the overall for the diagram in this case study. And so we have the gas bus for the gas storage to be like the input fuel for the OCGT power plant. So we go to the result. In this result, we can see the behavior of the storage. One of the highlight in this result, we can see the on the lower line is in the green color represent the CO2 from the atmosphere. We can see the CO2 from the atmosphere go down to 50,000 ton of CO2 because in this model we set up the CO2 limitation. You can see here. This is for the we set the case of the CO2 limitation is 50 ton of the CO2 equivalent, and when we run the simulation, we can see the graph is show we can fulfill for the CO2 reduction. This is from the atmosphere, and also to do this, we need some the CO2 storage because we cannot mitigate or we cannot reduce the CO2 from the atmosphere without using the carbon capture. We can see the amount of the CO2 or carbon capture increase. Yeah, this is the highlight for the simulation, and also we can see the trend of the value of the natural gas they use for in this snapshot. And so this is the biomass feedstock 1 and feedstock 2. You can see the software can choose for the biomass stock 1 and stock 2 based on the cost optimization. In the snapshot from the 0 to 6, we don't need to operate for the biomass stock 1, and for the stock 2 they do the operation based on the cost optimization. And so we can see the term of the diesel and the hydrogen as well. So this is like a validation. You can see the number of the carbon is constant. That means when we do the combination of the CO2 in the atmosphere, the CO2 from the carbon capture, and also the CO2 from the gas, when we do the combination of this one, and then we can get the constant of the carbon or carbon dioxide. Now I go to the last slide. Is the PyPSA is can show the production based on the cost optimization. We can see the production from the biomass 0, and also from the biomass 1, from the OCGT with the CCS, and we can see the operation of the direct air capture. And if you remember, Trisen said actually they have any information when we run the PyPSA, we can do additional consider not only the CO2 or the production. So that's all for my presentation. Thank you very much.
Thank you ค่ะ Dr. ณัฐพงศ์ for your detailed demonstration on how to use PyPSA to model the two examples that you have shown. Yeah, I think we start to understand more how PyPSA, what PyPSA look like, how it works. Yeah. Okay, so now it's time for the questions. Or if you would like to discuss something, if it's not a question, if you would like to discuss, please feel free to do so. I have one question for Dr. ณัฐพงศ์ for your presentation and the two example case studies. It's calculated all the modeling or optimization is based on the energy input output, right, and not considering the location. Am I correct?
Actually, if you remember, if we input the geographical potential from the IE zone into the one of constant, I think the software can be calculated for the cost optimization based on the location as well. It depends on the data when we input based on the data. But normally, the software will do calculation based on the cost optimization, and that's why we have to input for the capital cost, on marginal cost or O&M cost. I mean, for the marginal cost, it's based on the fuel cost and O&M cost, and then the software can do the optimization.
Okay. Yeah. And another and the next question is for Ipaleng. Actually, I wanted to ask this since last time about the wind potential. Because normally the wind potential, the higher the elevation, the higher the potential. I mean, this is in general, right? Like the wind speed is higher or something, and but when we select the suitable area for renewable energy installation, the elevation and slope has the opposite effect. So in your experience, when we select about the wind potential, which one have more effect to the cost or something?
Okay. So the criteria of the slope, when I said for wind, we potentially would like it to be less than 17 degrees. It was because there's a cost implication on the ability to construct it, because when the elevation is higher, that will also translate into higher costs. However, you are right in a sense that with higher the hub height, heights, there's more resource. But the two, I'm trying to. They're not. So the criteria I was referring to, they are not interrelated. We looking at the angle, the slope of it, which is the one that has a cost implication on it. Because you can think also when you are constructing those renewable energy plants, you will need to reinforce your foundations if it's not on a flat terrain. Not necessarily saying that the hub height is lower and that you are not getting optimal wind resource from it.
Okay.
And I mean, so if you mentioned that there's a lot of wind resources in the higher elevations, but I think you also find a lot of wind resource in mountainous regions, and that's, I think, just due to the shape of the land and how the wind is formed and moves within there. So there's certainly a lot of potential, and there's a lot of study that goes into finding some of these sites. So yes, it's difficult to get into these mountain ranges and some of these regions, because firstly you need to put transmission lines to get the power out of there, and that adds cost. But there's a lot of work that goes into strategically placing the wind turbines in some mountain ranges that don't have those extreme slopes. So when you get down to the details of individual plant siting, you can get efficiencies there to reduce costs somewhat.
Okay, I see. So there are many more factors to include. Yeah. Okay. Any other questions from the audience? Okay, there's one question. How can you optimize the spinning reserve capacity to meet the uncertainty of renewable energy and EV charging load in order to minimize the total cost? Yeah, I'm not sure this is to Paul or Tristan. Actually, the question is in the chat box, but I can read again. How you can optimize the spinning reserve capacity to meet the uncertainty of renewable energy and EV charging load in order to minimize the cost, the total cost.
You're on mute, Paul.
Just say a little bit, and then maybe the actual number crunching in PyPSA, Tristan can talk about. But the whole issue of reserve, spinning reserve, is quite a complex discussion, because ultimately it depends on the country's appetite for load shedding or outages. So the basis of calculating your spinning reserve is your loss of load expectation or your loss of load probability. So if you're prepared to, as a country, to have, say, 20 hours a year or 12 hours a year without electricity, then that can then derive into a reserve requirement. So the reserve requirement is coming up with your reserve requirement is not what's the word? Not superficial is another word. Is not a simple situation to come up, a simple calculation to come up with your reserve. Once you've got your reserve, say for instance you've decided that your reserve is the biggest trip of the biggest unit. So if you've got a 10 gigawatt system and you've got your biggest unit is a 500 megawatt unit, often your reserve can be calculated as the loss of that biggest unit. If that biggest unit were to trip, you would need to have sufficient reserve sufficient spinning reserve for your system to be able to withstand the loss of that biggest unit. Or you could have an interconnector, an interconnecting line to another country where there's 1 gigawatt coming in from that neighboring country, and then that becomes a trip of that line then becomes your biggest loss, your biggest single loss. And then you would need to make sure that you've got the reserve to handle that biggest loss plus more. But remember, if you lose a 500 megawatt plant and you've got 500 megawatt reserve, it doesn't necessarily mean that the 500 megawatt reserve is going to maintain your frequency to within correct limits. You need to actually run the Dix-Island frequency stability model to see if that reserve that you have got is fast enough and actually keeps the frequency within limits for the loss of that biggest infeed or the biggest loss of that biggest unit. So now we've established the size of the reserve. You can then put that reserve as a hard requirement into the PyPSA model. So you say to the PyPSA model, here's my demand. And as one of the constraints, Tristan mentioned constraints. So your constraints will be your thermal loadings, will be your minimum safe loading. Some plants have to run all the time. They can't be switched off. So you'll have all your constraints. And then one of your constraints will be this reserve requirement. So I don't know if Tristan wants to add on anything to that.
Yeah, so I think just when you are implementing one of these constraints in PyPSA, there's no line item that says this is how you provide the constraint of your reserve capacity. You need to use first principles to incorporate it into the model, and that might be in the form of increasing the demand that you feed into the system, and you know that you have your original demand and your reserve, and as long as PyPSA optimizes for that, you can be sure that your system is cost optimal for meeting demand and the reserve that you've defined.
So at present, it seems that, and I'm sure people are going to write routines that achieve this function. It's just a matter of time. But at the moment, there's not a field in PyPSA to say add 15% or 18 or 20% as a reserve margin. What you would do is you would add that to your demand, and that extra 15% to your demand, and you have to find a workaround to achieve the reserve, that 15 or 20% reserve requirement.
Correct, correct. And PyPSA is built to be as flexible as possible, so you can define how to incorporate that reserve margin as you want. There's many different ways. You can adjust the code as you see fit to do that.
And then just to add on to this discussion, remember, primary reserve is not everything. Primary reserve is important, but primary reserve gives you, which in the European Union, in INSTA, they call it FCR reserve, which is frequency containment reserve. It's basically spinning reserve, primary reserve. Once your governors or once your battery or whatever has compensated for that loss of generation, you also have secondary and tertiary reserve requirements. For instance, you might trip that generating unit at 4 o'clock in the afternoon when your PV is starting to ramp down. So now you've got an FCR primary reserve issue and you've got a ramping issue. So you need to make sure that your secondary and tertiary reserve is also sufficient to handle the ramping of the wind or the ramping of the sun as well. You're on mute, Dr. Sanira.
Thank you very much, both Paul and Tristan. Okay. Do we have any more questions? Yes, please, Ipaleng.
Well, thank you, Dr. Sanarat. I just wanted to add, based on the question you also had asked, to say that the fact that even though we have good wind resource on mountains, just to show the sort of incremental cost that could be added in you choosing such an area as your renewable energy zone. Obviously, that will also impact the costs of your roads, as grading has to be done to make sure that the equipment gets to be delivered there. The towers for your transmission lines, that the sort of topology that you will have to design your towers for. Yeah, there's just a whole lot of cost implications that are there. Not to say that you shouldn't build it there. It's just you assessing and trading off some of these criterias and all of that. Thank you.
Okay, thank you.
Dr. Sunila?
Yes, please.
Can I add
Yes,
some
please.
information for the? I think it's a very good question to think about for the reserve margin. And as we know, for the PyPSA, we rely on the cost optimization. But how can we include the number of the spinning, the reserve margin into the one of the constraint? This is the issue. I think it's really interesting question, and also, but in Thailand, if I do not mistake, for the new PDP, we'll use what LOLE is one of the for the reliability index as well. Okay, I will check how to include for the reserve margin, or the LOLE is one of the constraint for the PyPSA. It's really interesting question.
Yeah, yeah, LOLE, loss of load expectation.
Yes.
You're 100% correct. Yeah.
Yes.
Okay. So thank you for the question from the one of the audience.
Yeah.
Anonymous audience. Any other question, please? Okay. Or if the speakers would like to add something, yeah. Okay, if not, so this come to the end of the webinar too. So I would like to thank once again for all the speakers for the insightful information and valuable experiences that you share with us. And also thank for all the participants for attending this webinar and also ask the interesting questions. So I hope you enjoyed the webinar and found it useful. Your feedback will be valuable in helping us to improve our future events. So please complete the questionnaire by scanning the QR code, or as you can see here, or accessing the link provided maybe on the next slide. So, so we look forward to seeing you all in the next event. So have a nice day. Thank you. Bye-bye.
Thank you.
Bye.
Bye-bye.
Bye.
Thank you and bye-bye.
Thank you.
Thank you.
Thank you.